Go.
Good morning, ladies and gentlemen. So far we've been, missed the pipe. We've been playing with our resonators, a closed pipe.
And it's closed because you got your hand on the end.
And what's going on with this though?
You get a different sound when you take your hand off.
Yeah, why do we have that? So let's talk about it. A resonator, I think they cleaned the floor here. A resonator reflects waves back and forth at a particular frequency, forming a standing wave inside of our resonator, right? It's a standing wave is between here and here.
Yep.
Okay, resonating back and forth. Our standing wave is in there. A closed pipe resonator has different parts of a standing wave at either end. A node and an antinode.
It's because you've got different situations at either end. One end is closed, one end is open.
Yeah.
So you get the different parts of a standing wave at the different parts, the different ends.
And what are those parts? So this is a standing wave here, and this is one wavelength.
Yeah.
And what part what part would be inside of our closed pipe resonator? Well, a node to an antinode.
Yep.
And how much of the wavelength is that? 1, 2, 3, 4.
1/4.
A fourth of it, right? There is a quarter of a wavelength between a node and an antinode.
And we did that yesterday when we found the frequency of the pipe. When we just used the length of the pipe, assuming that was a wavelength, we got nothing.
Yeah.
We got the wrong frequency, but when we multiplied the length of the pipe times 4,
It's really 4 times as long.
that's right,
Right,
then we got the right frequency. So that proves that this is true.
If a closed pipe resonator has a quarter of a wavelength in it, how long is the whole wave?
I think we just answered that, but
answered
let's
this.
see the illustration.
Yeah. It would be 4 times as long, right? So if this is the pipe right here, okay, this is the length of our pipe.
Yeah.
We've got a quarter of a wavelength in it. The actual whole wavelength is going to be 4 times as long. Boop, boop, boop. Right
Yep.
here. So that's the whole wave.
So the wavelength is 4 times the length of the pipe.
And now something new. An open pipe resonator is the same at both ends. How much of a wave will fill it?
Well, the open pipe resonator is when you hit it and took your hand off, right?
Like this, right? And so in that case, it's open at both ends,
Yeah.
right? That's what we're saying here. So what was the question again?
How
much
much?
of a wave will fit in it? So we said it's the same at both ends?
It's the same at both ends.
Okay, so that means it has to be either a node and a node or an antinode and an antinode,
Yeah.
right? So how much of a wavelength is between a node and a node?
I know. Half a wavelength.
Half a wavelength, right? And same thing for this, right? From here to here, okay, that's half a wavelength.
Yep.
An open pipe resonator has the same parts of a standing wave at either end. So an antinode and an antinode.
And I think that was in the reading that they did.
I think so too.
Yep.
Okay. And here we are. So this is our our pipe, and we can
It's an
see
antinode at one end and antinode at the other end.
Yeah, they're both. It's antinode on both sides. Same thing on both sides. And because of this, like we said, we can fit half a wavelength in it. And how do we get? So here's our equation for frequency.
Yeah.
Velocity over our wavelength, right?
Yeah.
And we put 2L here. Why have we done that?
Because the whole wave is going to be twice as long as a pipe.
Yeah, and if you're a math person, you just multiply by 2 on both sides, and that's how you get it. Or
Even if you're not a
visual
math person, you can do that.
Yeah, if you're a visual person, you can see it, right?
Yeah.
However
Yeah.
you think, right? The fundamental frequency for an open pipe resonator is 1/2 a wavelength. So before, for our closed pipe, our fundamental frequency, our most basic fundamental frequency was always going to be 1/4 of a wavelength.
Yep.
Now, it's half a wavelength, and that's where we get that sound.
Can we find the frequency? What can we find the frequency? What was that thing in that previous slide?
Oh, this one right here?
This one right here. We can use this to find the frequency
yeah.
because
And you know, let me just go ahead and write that on the board. Okay, so frequency equals velocity over, instead of 2L, I'm sorry, instead of 4L,
we had 4L for the
closed pipe,
closed pipe.
we've got 2L because it's half a wavelength.
Let's.
What is our task? What have we been tasked with? How long is the whole wave for an open pipe resonator? Find the frequency. So first of all, let's find the length for a whole wave of this one right here. Okay. So from here to here, boop, 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 boop. Let's call that 34.7.
I like that.
No, yeah, 34. I said 34, right?
34 points at 0.347 meters.
Okay. Oh, so that's centimeters, right?
Yeah.
So that equals 0.347 meters.
Yeah.
And what do we have to do with this length?
Well, multiply it times 2, and we'll use 343 meters per second as the velocity of sound in air.
Where's my thing? Okay. So 0.347 times 2, and I get 0.694. Okay, so, and then we said we're going to use 343 for, because it's 20 degrees Celsius in here, right?
Could be.
Okay, we won't check. Okay, and so 343 divided by our answer gives me 494 seconds per second.
494 hertz. And of course, we don't have the online tone generator called up
I know.
to check it out.
Should we get it? Should we do it?
We should. That'll only
Yeah.
take a moment.
Okay, and that's for this one. Okay, oh, mousy. And I've got it saved too, so this more is now prepared. 494.
Yeah.
This Moore's computer is slower than it used to be. Okay, here we go. So first of all,
That's pretty close.
here we go. That's all better. Okay, and stop. It's pretty close.
It's pretty close.
Right? So should we have them do their own?
Yeah, here's another one.
Okay, so we'll say that this one is 45.9.
So this one is 45.9 centimeters. That's 0.459. Calculate the frequency of the open pipe for this length.
Do it.
All right.
That's you guys. All right, so what's next?
Now we go to complicated stuff.
Resonators have more than one standing wave in it.
Yeah.
These are called the harmonics. We saw the same exact thing for, not the same exact thing, but the same idea with closed pipe pipes.
And the idea is that the loudest sound you hear is the fundamental. And all these others are there, or maybe there, and they add to the quality of the sound.
Yeah, and do we want to go into the counting them or no?
No, I don't think it's important. I think the most important thing is to know that there are harmonics. For example, all of these have a node at either end, a node at either end. And
before, for the other ones, it was like this.
yeah, for
like
a
that.
closed pipe.
It was like that. But now we've got half a wavelength instead of a quarter. Okay.
Yeah.
All right, so let's talk about this diagram here. So, this is a little bit more complex. It says included harmonics add together to alter the resulting sound wave.
So what you've got here is you've got
So you've got three different frequencies.
yeah,
right?
the red here is the
four.
sum.
Sorry, we go. Oh no, the red is the sum.
And you've got the green one here, that's the fundamental.
Oh
That's the longest wavelength. And then the blue one is the third harmonic. Notice that the blue one has a shorter wavelength. The yellow one is the fifth harmonic, which is even shorter. And so they all add together and constructive and destructive interference. And the net result, what you actually hear is that red line.
And why is this a good thing? Because it sounds good.
Yeah, and it different musical instruments can play the same frequency, the same pitch, but they sound different because of the mix of harmonics that are going on at the same time.
I think that's all we're going to say about that for now. Okay. More complex resonators produce many frequencies that add together to produce a unique sound. And that's what we saw there.
Yeah. And we've got an YouTube example here in the next one. This is the most obvious musical instrument that contains
open link, that's what I want. Come on, Wi-Fi, come on. You can do it.
the instrument that really shows that you can hear the mix of frequency is the steel drum, or the steel pan drum. And it is was invented in
my Wi-Fi is really slow.
Yeah,
You
but
guys remember me complaining about my Wi-Fi? Okay.
All right, start it over again.
If it'll let me here. Hold on. Now my volume is off here. Hold on. Thanks. Okay, pause. Volume on. Okay, start over here and
Notice how ragged this sound is? Every note, you can hear there's a bunch of things going on at the same time. Cool. It's all about harmonics. Okay.
all right, so for your guys' homework today, now we really are going to have you do number 6. 6 A, B, C, and D. Go ahead and do it.
You can do this.